How are you, everybody who is watching this video? I'm very happy to have you today, and I would like to take this opportunity to welcome you into a very interesting moment of learning about digital electronics. It's the first time to meet me. My name is Olenjolai. I am a Tanzanian. I thank God for the gift of teaching and being electronics and telecommunication engineer. I would like to take this opportunity to welcome you into the moments of learning about basic logic gates. I want to tell you that in advance, this workshop will transform your life, and especially if you have the fundamental skills of electronic science about fundamental or about basic logic gates. We call them sometimes basic logic gates or fundamental logic gates. In case you have missed about other previous workshops, you should not worry. I will just give you the instructions how you can access them and enjoy, because always electronics or digital electronics, it's not a simple field, but we who have been called for that, we always enjoy them, regardless that they are most challenging sometimes, and sometimes just they can make you that unhappy. So I have some physical students and a number of students in this class. I would like to appreciate their presence. For the online student, what are the requirements for this lecture or for this workshop? Just a fresh mindset, an exercise book, a pencil, a pen, a rubber, and then refer about the previous electronic science that you know. So I think that you are ready. Let us appreciate some physical students, and then we are going to workshop number 3. How are you, students? How are you, engineering students? Well, are you ready for workshop 3? Wonderful. So let us start with quick review of workshop 2. So in workshop 2, first of all, we talked to you about the definition of logic gate. And then you say that logic gates, these are the digital. This is the digital electronic circuit that perform Boolean operation. When you say Boolean operation, we'll discuss them later. And then we discussed that there are the 2 types of the logic gates. The first one, there are 3 types of logic gates. So I told you about 3 types of logic gates. Class A, 3 types of logic gates. So the first one, we call it basic or fundamental. So we call them basic or fundamental logic gates. Basic or fundamental logic gate. The second type, we call them universal logic gate. Then the third type, we call them exclusive logic gates. And I gave you 7 examples. Then I gave you 7 examples. I present to you 7 examples of logic gates that we have in digital electronics. The first one is what? NOT gate. The second one is what? AND gate. The third one is what? OR gate. The fourth one is what? NAND gate. The fifth one is what? NOR gate. The sixth one is what? Exclusive OR gate. Yes, exclusive OR gate. Then the seventh is what? Exclusive NOR gate. So remember, NOT gate, AND gate, OR gate. These are what we call them fundamental or basic logic gates. Then remember that NAND gate and NOR gate, we call them universal logic gates. Exclusive OR gate and exclusive NOR gate, we call them exclusive logic gates. Then I said, okay, let us start to discuss about NOT gate. And then we discussed about NOT gate. I think that we learned what the means of NOT gate and what the means of NOT gate. NOT gate or NOT logic gates, it's a type of fundamental logic gates which perform inversion of the binary inputs. Then the second concept that I taught you, the schematic symbol of NOT gate. And I taught you 4 different symbols of NOT gate. Two of them are IEEE, according to IEEE, and 2 schematic symbols are actual that we call them American schematic symbols, which are using rectangles. Are we together? Then afterwards, we discuss about we call it the schematic circuit diagrams of NOT gate. And the next concept, we discussed about timing diagrams of NOT gate. And then the next concept, we discussed about Boolean algebra of NOT gate. And then we discussed about the physical appearance of NOT gate. But the physical appearance of NOT gate, I made a mistake. So I want to correct. So today's, let us start where I made a mistake to make correction. Are we together? So if you miss workshop number 2, you should not worry. We will publish that video on 1st June 2024. At what time? At 11 a.m. in Tanzanians or East Africans hours. So, physical appearance. Physical appearance of NOT gate. Physical appearance of NOT gate. Say physical appearance of NOT gate. We know about the schematic symbol of NOT gate. This is the schematic symbol of NOT gate. Well, that's what we've been dealing with it. But what the physical appearance of NOT gate, in case you want to use the NOT gate in our digital electronics design process, how does it look like? And how can we find it? Okay? So the physical appearance of NOT gate, I just gave you one of them, or just one of the physical appearance of the NOT gate. And then after that, I made a mistake. So this is the correct one. So for those who have been in previous class, make correction about this physical appearance. First of all the NOT gates all the NOT gates are always found in integrated circuit. Say integrated circuit. Say integrated circuit. And I told you that in electronics we have through-hole integrated circuit and surface mounting device integrated circuit. Right? So this is through-hole integrated circuit. So NOT gate, most simple NOT gates are made within the integrated circuit with 7 pins. With 7 pins. So this is the first, second, fourth. So here we have another pin, and here we have another pin, and here we have another pin, here we have another pin, and here we have another pin. So for you, you have to make sure that this pin is in straight line with this one because you have a ruler. For me, just I've drawn it roughly by using a hand. So this pin and this pin should be in a straight line of 180 degrees. Similarly for this pin, similarly for this pin, similarly for this pin, similarly for this pin, similarly for this pin. How many are those pins? How many pins do you have? 14. So this one, we call it a notch. A notch, this is the universal. It's a universal mark of any integrated circuit that actually gives us a universal or a unique ways of numbering the pins of any integrated circuit. So whenever you are dealing with integrated circuits, whether through hole IC or surface mounting device IC, you have to make sure that you identify the notch first. Otherwise, you will destroy it effectively. Ruben, where is Phil? So this is pin number 1, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, and pin number 7. So once you identify the notch, then you have to count, or you have to number the pins in anti-clockwise direction. This is clockwise direction. We have learned the concepts of clockwise direction when we have been learning physics from 2, when we've been learning about equilibrium. And we learned the principle called that the total clockwise moment should be equal to the total anti-clockwise moment for the system to be at equilibrium. So numbering of any integrated circuits should be what? Anti-what? Clockwise. Remember that this is clockwise, the same direction with the direction of arrow of the clock. Okay? So this is pin number 1 nearby the notch. Pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, pin number 7. And this one pin number what, class? 8. This is pin number what? Then county. 11. Then 13. Then 14. This is pin numbering. So if this is the process of numbering the pins, then this is what you have to do. At this point, we are going to assign, or each pin has its own name. This is the pin numbering. This is the number of the pin. It's not the name of the pin. And remember that, so this pin is called the 1A. And this one is called, its name is called the 1Y. And this one is called the 2A. And this one is called the 2Y. And this one is called the 3A. And this one is called the 3Y. And the name of this pin is called the this one. Okay. So then now, the symbol or the internal structure or the schematic symbol of NOT gates is just like this way. So this is the first NOT gate. And then we have the second NOT gate. Have the second NOT gate. Then we have the third NOT gate. This is the third NOT gate. Then remember that always the 7 pins for any NOT gate, it's the ground, where we connect the power, so the negative power supply. Then this pin, so I think that that's the point where I made a mistake. So for this case, pin number 8, it's called the 4Y, while pin number 9 is called the 4A. So in pin number 9, this is the configuration. So I reverse the direction of of NOT gate of this second part of IC. So I reversed it. So instead of having a NOT gate here, or it means that I reversed. Pin number 8 was input, and pin number 9 was output. That's the mistake I made. So you have to reverse. Pin number 9 is input, and pin number 8 is output. Are we together? Then again, for this point, we have another NOT gate. Then for this case, we have another NOT gate. So how many NOT gates do we have? 6. So if you have 6 NOT gates, so remember that the mistake I made in previous workshop, I just reversed the directions of the NOT gate. So that's why you have to do correction. And then remember that in each NOT gate, or each NOT gate has its number. Has its number. Which for this case, it's SN 70 what class? 74, then what? HC This is not gate number 04N. If you want to search it in Google, you just write that not gate IC number. And I told you that because you have 1, 2, 3, 4, 5, 6. So count it together. 1, 2, 3, let us go. 6. This was figure what? So for this case, this is figure 1. The physical appearance. The physical appearance of SN74 HC04 and naughty gate. So because we have 6 naughty gate, that's why that this one is also, we say that a naughty gate is also known as hex inverter. So what the meaning of hex inverter? Hex means 6. Right? A mono means 1. Bi means 2. Tri means 3. Tetra means penta means hex means. So this is called the hex inverter logic gate. So why it's called the hex? Because we have, it consists of 4 or 6 logic gates. This is what we did not teach you in the ordinary diploma. We did not teach you in A-level education. Because by God's grace also, I am a teacher of advanced physics. So I know the contents of what we have taught you. And by God's grace also, I am a teacher who teaches ordinary diploma students. So I know your background. So this is the physical appearance of 40 of NOT gate. So he said that simply an IC of any NOT gate consists 6 NOT gates. That is an important point. Then the last part that we have discussed about the NOT gate, it's how can we verify the truth table practically by either using electronic simulation software or practically when we have that NOT gate integrated circuit. How can we verify the truth table? How can we see that the NOT gate do inversion of the input? And remember the limitation of NOT gate? All the NOT gates have only single input, single output. Bear that in your mind. So how can we verify? Remember that the truth table, so he said that verification of a truth table, verification of a truth table of SN74 HC04 and NOT gate. And let me just say that we perform this business practically. So he said that in order to verify the truth table, in order to verify the truth table of the NOT gate, then the the binary input should be supplied to the input of the NOT gate. So in order to verify, in order to verify the truth table of NOT gate, then the binary input should be supplied to the input of the NOT gate in order to have verification of it. Remember that? The truth table of NOT gate, let me just remind you because you want to verify it. The truth table of NOT gate is simple. Just has two binary input. So we say that this is input, this is output. And then you have just the two states. When you introduce a binary bit of 0, the NOT gate inverts it to 1. When you introduce a binary bit of 1, the NOT gate inverts it to 0. So how can we verify it? So remember that we may verify the truth table of NOT gate by using some digital inputs parts, such as a digital sensor can be the one which supplying the input to the NOT gate. But just simplify the concept because possibly you have no any idea about digital sensors. We can simplify the concept in this way. We can use just pull up or a pull down resistor. Say pull up or pull down resistor. Again, say pull up or pull down resistor. No. Again, say pull up and pull down resistor. So you say that. So the source of binary input, binary input or binary inputs may differ according to the application. According to the application. So the following are some examples of the source of binary inputs. So the first one, we can have a binary input from the pull-up resistor. We can have a binary input from the pull-down resistor. We can have a binary input from a digital sensor. We can have a binary input from the pulse generator. We can have a binary input or the source of the binary input from logical toggles, etc., etc. Remember that what we are discussing now, we are focusing on practical. And when we focus on practical, we don't think that, because we have 0, we just see, we have 0, we'll get 1. Or 1, we will get 0. No. We have to think that 0, what does it define? And 0 and 1, what does it define? Okay? So these are the few examples that actual can supply a binary input Class, say pull-up resistor. Say pull-up resistor. Say pull-up resistor. Say pull-up resistor. Again, say pull-down resistor. Remember that when you pronounce this terminology, you are right in your mind. You don't need actual to spend the whole night to review this stuff. Say pull-down resistor. Class, say a digital sensor. Say pass generator. Say pass generator. And then say logic toggles. Again. Okay, so I think among these sources of binary inputs that you are familiar is something about resistor. So now ask your neighbor, what do you understand about pull-up resistor? So ask your neighbor, what do you understand about pull-up resistor? Is it a resistor that pulling up what? Or pulling down what? So for this module and for just the actual that taking the theoretical concept to practical concept for this module, we are going just to use the pull-up resistor and pull-down resistor. That's all. We won't discuss about a digital sensor. We won't discuss about pass generator or logic toggles. We just need this one. These are the two that we may use as our binary inputs. Because remember, if you don't have input, don't expect to have output. That's the principle of engineering. Whether it's mechanical engineering, whether it's mechatronic engineering, whether it's electronic. In case you don't have input, don't bother yourself to find for the output. And it's a fact of life. If you need output, make sure that you have input. Pull-up resistor. Say pull-up resistor. Yes, that's why I told you that. I know that you know. You have learned something about NOT gate. But you are still a scienticity and even a theoretical scientist about NOT gate. We are just discussing a simplest gate compared to others. So I told you to ask your neighbor, what do you understand about pull-up resistor? So what did your neighbor tell you? Nothing. I told you that be careful on choosing the neighbors, especially in all my classes. Try your level best to choose neighbors who can help you. Isolate yourself from neighbors who cannot help you to answer the questions. So write down, what did your neighbor tell you? Write down, just in rough. Write down. Even if the sentence is pull-up resistor is a pull-up resistor. That's fine. It's a response. I know now your neighbor does not show any cooperation. Your neighbor seems like busy. Writing and repeating writing pull. So for instance, if your neighbor is written pull up, then your neighbor is still writing pull, P. Just wasting for what? For time. Because there is no idea about pull up what? It's a new vocabulary. Well, pull up resistor is just nothing. It's simple. Stop writing. A pull up, say again, pull up. A pull-up resistor, we say that, is a network of is a network that consists a resistor and a push button. Just to simplify for you, a push button to provide only two states of high or 1 or 5 volt, and the low or 0 or what? 0 volt. That's the meaning of pull-up resistor. So class, what is pull-up resistor? 1, 2, 3. Stop writing. A pull-up resistor is what? So I believe that you know something called the push button, because always you are pushing or the buttons of your keypad on your mobile phone. So, and the resistor also, you know about potential divider and whatever. You have done a lot. So that's why I told you that a pull-up resistor is actually nothing. It's just a network of the 2 electrical or electronics components. A push button and what? A push button and what? And a resistor. So these are the application. For instance, if you are your friends who is actually pursuing maybe Bachelor of Law or Bachelor of Accountant, will challenge you. Yeah, we have been learning about resistors. Well, we have been learning about capacitors. Where are we applying them? Then you can tell them one of the applications of resistor is in designing pull-up resistor. So, the schematic circuit diagram, because I told you engineering is all about what? Class, engineering is all about what? It's all about what again? What? Robot? It's all about pull-up resistor. Engineering is all about numbers, or all about what? Graphs. And we had an agreement with you that whenever we meet, you have to ask your neighbor to show you at least one graph, one engineering graph. So now it's the time to ask your neighbor at least one graph that your neighbor has drawn it from the beginning of the week until today, which is Thursday. So now it's the time. Ask your neighbor, show me your graph. If your neighbor does not have a graph, it's a good sign that your neighbor is a political what? Your neighbor is a political what? So tell your neighbor, my neighbor, I advise you, please transform yourself from political engineer into a practical what? So tell your neighbor. Who are you telling to transform yourself, herself or himself? Stop writing, stop drawing. Look on the blackboard what I'm drawing. Pull-up resistor and pull-down resistor, it's very important phenomena in digital electronics more than you think. I said, stop writing. Take a pen of your neighbor. Take a pen or pencil of your neighbor. Tell your neighbor, now it's the time for listening. So this is the schematic circuit diagram of what? Of pull-up resistor. This is what about pull-up resistor. Hello? Oh yeah. So this one, it's a resistor, or it's a schematic symbol of resistor. And this one is a schematic symbol of the push button. Another schematic symbol of a pull-up resistor can be drawn like this way. So this is the push button. This is resistor, and this is ground. And this is figure 2. The pull-up resistor network. Okay, so these are the schematic circuit diagram of pull-up resistor. I said stop drawing. I said stop drawing, listen and watch. Remind your neighbor on my behalf. With this pull-up resistor network, it's simple. Let me explain about this network. Do you see your neighbor? Check your neighbor. So in this network, this is VCC. Say VCC. Simply, we say that this is positive for DC power supply. It's just like in NotGate, we had the pin number 14 is called the VCC. And I told you these abbreviations of voltage across collector for the bipolar junction transistor. Are we together? And then the second part, it's ground. This is the schematic symbol for the ground terminal. When you talk about ground in digital electronics or in electronics, we mean it's negative terminal. Whenever you have, for instance, a battery or a cell, it has two terminals, positive terminal and negative terminal. So the positive terminal of the battery, it is the one that we call the VCC. And the negative terminal of the battery, it's the one that we call the ground. That's all. Are we together? Yes. Are we together? Yes. So nothing new. You are familiar with every components and symbol which has been drawn there. So listen, the plenty where we used to actual that to test about the pull down resistor or the pull up resistor, it's this one. At this point, we are going to have this is the point where we are going to draw our output voltage towards the input of any logic gate. So another component, do you see your neighbor Edgar? Another component is resistor. Say resistor. Say resistor. And another component is called the pushy button. So this is pushy button. Say pushy button. Again, say pushy button. Again, for the second or for the figure number 2B, we have, do you see your neighbor, my sister there? We have also what VCC, which is positive DC power supply. And we have ground, which means that negative terminal or negative of the power supply. Ruben, you are Rubening. Then here we have also two components. The first one is resistor, and the second one is push button. But remember that also for this, for the figure 2, Roman B, this will be our V output. We draw our output between the resistor and the pushy button. Say pushy button. So how does it work? If we use a voltmeter or DC voltmeter, Japheth, you are Japhething. So, if you use a voltmeter, for this case, when the push button is pressed, then the potential difference across this push button will be 0. What did I say? What is my last sentence? You wasn't in the class. Keep this for me. I said, when the push button is pressed, say it's pressed. It means that the push button is closed for this case. When we have VCC, for instance, it is, let's say, 5 volt. Okay? For that case, then the loop will be closed. Why the loop will be closed? Because this is the positive supply. The current will be flowing through resistor, and then it will face some resistance because of this resistor. And then the current will be flowing through the push button and be flowing through the ground, and then the loop will be closed. So if the loop will be closed, all the currents that be supplied on the positive terminal of the power supply will be drawn to the ground. That's why the voltage output for this case will be 0. Are we together? For this case, remember the push button is not pressed, it is in open state. So when, for instance, that the power will be flowing, this will be open circuit. So because it will be open circuit, what we say? The VCC, the current will be flowing through the resistor, and it will be flowing up to this point, but this point is disconnected, or it's open circuit. It's open what? Circuit. So because it's open circuit, there is no flow of current from this point to this point. And remember that current cannot flow wirelessly. Are we together? For that case, there is no flow of current from this point to the ground. Then, if the supply voltage is 5 volt, the potential drop between this point and the ground will be 5 volt. So this will be low state or high state. This will be high state or low state, depending on how you are actually configure, just choosing the 5 volt to be either 1, binary bit 1, or binary bit 0, depend. Are we together, class? So for this case, if for instance we have supply voltage of 5 volt, then if you have a voltmeter, then I'm going to connect the voltmeter. If you have a voltmeter connected here, so this is voltmeter across, or voltage across the push button when it's pressed. That means of VPP. If you measure the voltage, and you will measure it practically, you will see. If you measure the voltage across this push button for this case, so VPP will be 0 volt. So if it will be 0 volt, you can say that this 0 volt, I will call it bit number 0. Ha ha ha. Yeah, resistor is good. I know that you are saying, sir, can you repeat a little bit? Because you just see 0, 5, 0, 5, 0, 5. Okay, this is still introductions of digital electronics. But I know when I mention not yet, as I say, then let me tell you, hey, 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 hey. Okay, let me repeat. Should I repeat? Okay, listen now. Should I repeat? Listen, careful. Listen, I said, this is positive terminal. It's just like, let me just show you a symbol of the cell to remind you about positive and negative terminal. This is negative, this is positive. You agree? So the positive terminal of the cell is what we call the VCC. The negative terminal of the cell is what we call the ground. And remember that currents always flow when the loop is closed. And you learn that concept in Kirchhoff a lot and much. You used to choose what? Closed loop. When the loop is open, no flow of current. And that loop where the closed loop we have, we call it short circuit. And the loop which is open, we call the electrons open circuit. Are we together? So let me explain. When I'm on this side, we say the supply voltage supposed is 5 volt. So then the current will be flowing from this point, from positive terminal of the power supply towards it. You say it, let me repeat, but you are drawing. Look your neighbor. He or she said that, repeat, sir. But when I'm repeating, he or she is drawing. She's busy on drawing. Let me draw. Okay. This is supply of 5 volt. Right? Right? Right, Ruben? Ruben is Rubening. Are you Ruben? Okay. Then, so the current will be flowing towards a resistor. This resistor will actually oppose the flow of current. And then we have a flow of current up to this point. Remember, this is open. There's no flow of current on this side. Then we have a flow of current up to this point. Remember, the push button is pressed. The push button is what? Pressed. So when it's pressed, it means that this is the closed loop. So the current will be flowing from this point to this point towards the ground. And then return back to the positive. And then it will be circulating continuously. That's the first point I made. Is it clear? Is it clear? Is it clear? So because this point, it's actual, or this we call the closed loop, and at this point the push button is connected, there is no potential drop here because resistance is 0. So because resistance is 0, all the 5 volt will be drawn towards the ground. Is it clear? These are the fundamental inputs of all the logic gates that we are going to discuss. What does it mean? It's very simple. For you who have been going in A level, let me just use this style to explain it to you. Suppose that you have 2 resistors. This is R1, this is R2. And then here you have a supply voltage. So if that's the case, we'll have V across R1. Let me just remind you because I love you so much. And I know what you taught in A level, but unfortunately for you, you have forgotten. Right? Right? Suppose R1 is R. Suppose R2 is push button. Then we taught you the concept of potential divider. Say potential divider. And that's the application of potential divider. But for you have been applying on answering the questions for next exam. According to the principle of potential divider, Faustina, according to the principle of potential divider, we used to say, or according to the Ohm's law, we used to say the supply voltage is equal to what? VR1 plus what? VR2. Because the resistors are in series, then we say what? Current is the same. So if the current is the same, we call it I. I times what? R1 plus I. R what? R2. Then supply voltage is equal to what? I is constant. Take it out of the bracket. R1 plus what? R2. I say this stop writing. Because you didn't understand what I've been explaining to you. When I was explaining to you, you are responsible to recall potential divider and connect what I was telling you to say. Yeah, sir, you are right. But because you don't connect yourself, then you are disconnected all the time. Let me remind you. Okay? Make the current the subject. Say supply voltage of R1 plus R2. Those days, when you've been a good physicist, you used to call this equation 1. But nowadays, no. You don't have equation 1 or equation 2 or equation 3. You just say right, because it's none of your business. You do fire extinguisher, and then you extinguish the exam. So just to arrange your work, that's none of your business. You may write answers without solution. Do you know yourself? You may write answers without what? Solution. Okay. Voltage across R1 will be what? Total current times R1. Right? This one we used to call what? Equation 2. When you have been a teenager. Nowadays you are an older man or older woman. Right? Then we used to say that substitute equation 1 into equation 2. What do you have? the voltage across R1 is equal to what? Supply voltage of R1 plus R2, then times what? R1. And we are very good to arrange resistors themselves in order to cancel ohm plus, and ohm. Then you have been writing something like this. Is isn't? Is isn't? Eh? It's correct, yeah? Let us come back here. So we used it to say that let R1 is equal to R. Let R2 is equal to push button. Let us verify what I told you. Because I know some of you have argument. Ah, sir, you are lying to us. Are you lying to us because you didn't do practical of digital? No, I'm not lying to you. Okay, so if that, okay, so this one, it's what? How does it work? So for this case, remember, push button, hello, is not depressed. Say it's not depressed. So for this case, resistance of resistor still R. Hello, check your neighbor, check your neighbor. Your neighbor is writing formulas of potential divider. For this case, resistance of the push of the resistor, it's R. And the resistance of the push button, it's infinity. Why is infinity? Because it's open circuit. So whenever you have open circuit, the current cannot flow because the resistance between the 2 points is infinity. Japheth is Japheting. Japhet is what? Japheting. Stop here. Okay, so let us keep forward or keep moving with lecture 3. Lecture 3, which is all about basic logic gates. So I have told you about the physical appearance of the NOT gate, and also I have told you about the pull-up resistor network. So now we have to make sure that we have the schematic of a raw schematic circuit diagram where we can use a NOT gate to invade, just to do inversion of the signal or inversions of the digital signal. So with that case, we say that schematic circuit diagram, schematic circuit diagram of what the IC number of that NOT gate, HC, what is 74, what is? There? What the IC number of that NOT gate that we have been discussing? Eh? Pardon? What? SN. SN 74 HC04. SN 74 HC04N. So this is NOT gate. Well, so if you do remember the general block diagrams of the any electronic system, we have the power supply unit, we have the input unit, we have the control unit, we have the output unit, right? So for this case, we don't bother. The power, the power supply will be just a DC source. So we have to draw first of all the physical appearance of this logic gate, which it is not logic gate. So this is what we call T-notch. And then you have the first pin. There are 7 pins, if you do remember. The third pin, the fourth pin, the fifth pin, the sixth pin, the seventh pin. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So if you do remember that, we have 6 NOT gates. Then also you have another one. No. Yes. Also you have the second NOT gate. Also you have the SEDI NOT gate. Please make sure that you draw the internal structure of the NOT gate for your comprehension. And for this one, we have ground pin. This is equal to 1A. This is 1Y. This is 2A. This is 2Y. This is 3A. This is 3Y. For this side, we have also these kinds of the configuration. There are 3 NOT gates on this side. This is 4A, 4Y. We have another NOT gate. So this is 5A, this is 5Y. Also for this case, we have another NOT gate. This is, 5A, 5Y. For this case, you have 6A, 6Y. Okay, so this will be our control unit, but this pin we call it VCC, voltage across collector terminal. Ruben, please update the venue and the time. Okay, so this will be our control unit. So for the VCC, we have to power or to supply power into our electronics component. Then for this case, we'll just need to get the VCC, which you have to connect a 5 volt to supply 5 volt according to the manufacturer. And the ground pin, we have to connect to the ground terminal. So the ground is corresponding to the negative voltage terminal of the power supply. After that, we need to use at least one of the NOT gate to invert the digital signal. So I told you about pull-up resistor. So for this case, you have VCC. Then here we have a pull-up resistor itself. And also we have a push button. So this is push button. So we have to take some potential difference from this point and connect it with the pin number 1. Then the NOT gate will invade these bits. It might be either high or low, depends the state of the push button. This is resistor. And I think that we specified, we said that we are going to use 10 kilo ohm or a resistor with resistance of 10 kilo ohm or 1 kilo ohm. Then we have to take the output from the NOT gate number 1. How can we verify the output? We may use the light emitting diode actual to give us indication about the inversion of the bits. So this is LED, and this LED will be acting as the output. So let's give indication about the output or the status of the output. So how does this circuit? So this is the input. The pull-up network will be acting as the input. Pin number 14 and pin, because this is pin number 1, number 2. So 1, 2, 3, 4, 5, 6, 7. And this one is 8, 9, 10, 11, 12, 13, 14. So this pull-up network will be actual acting as the input to our NOT gate. You may use the first NOT gate. You may use the second NOT gate. You may use either the third network. You may use the fourth NOT gate or the fifth NOT gate or the sixth NOT gate. You may use all of the NOT gates in case that, depending on your design. So these 5 volts supplied to the 14 pins and the ground terminal supplied to the pin number 7 will be acting as the DC power supply to this HC, we call it S, and 7, 4, H, C, 0, 4, N. And this one will be acting as OT. And this one, this pin number 2, will draw the output. So this is power supply, this is input, this is output, this is a controller. So the control unit for this system is NOT gate number 1. And I've explained. If the push button is not pressed, then the output voltage or the potential difference across this point will be, because we have to do measurement, the potential difference across this one, across push button, we say that it is what? 5 volt, right? So you can actually say that, okay, according to your design, 5 volt representing bit number 1, and 0 volt will be representing bit number 0. So if the push button is not pressed, so the bit supplied to the input of the NOT gate is bit number 1. Is that the case? Then the NOT gate will invade this bit, because remember that the truth table of the NOT gate, it has actual 2 columns. One column is input, the other one is output. Then we say that if the input bit is 1, the output is 0. If it is 0, the output is 1. So if supply a bit of 1, we expect it, if the NOT gates will be working, the output will be 0 volt. Right? So if it will be 0 volt, remember 0 volt correspond to bit number 0. So 0 volt will not be able to turn on the light emitting diode. So this one might be a resistor, which is resistor. Let's say that it's 220 ohm. That's the resistance of this resistor. So if the output voltage from the NOT gate is 0, it won't turn on the LED. So the LED will be off. Then we press the push button. Once we press the push button, the state will change from 1 to 0. Because when we press the push button, the potential difference across this push button, it's 0. So when the bit of 0 supplied to the NOT gate, then the NOT gate will invade that bit, and the output bit will be 1, and 1 corresponding to 5 volt. Right? So if you have 5 volt, the LED will turn on. So this LED actually will give you the status, the two status or the 2 states of the OT of the NOT gate. Are we together? Are we together? Are we together? So from this fact now, from this figure, we can verify the truth table of the NOT gate. And this one we numbered. It was figure number what, Edgar? Figure number for those who have written, because figure number 3. So the schematic circuit diagram of SN74HC04N NOT gate. Then I think that we didn't discuss this part, principle of operation. Principle of operation of figure of this schematic circuit diagram. So its principle of operation, yes, it has 2 principles. Just the two principles according to the truth table. So the first one, we say that when the push, class A push button, class A push button. So when the push button is not pressed. So when the push button is not pressed, we say that then the input voltage, because remember that for the VCC, it should be 5 volt, according to the data sheets of this IC. The input voltage is 5 volt. So it's 5 volt. So then we say that it is supplied it is supplied or it is fed. So this 5 volt, say that when 5 volt is fed into the first NOT gate, then the NOT gate invade the NOT gate invade the input voltage to 0 volt. The LED, for that case, the status of LED is off. Why it is off? Because there is no any power supply across our light emitting diode, because the output of the NOT gate is 0 volt. So if it's 0 volt, 0 volt cannot turn on the light emitting diode. Okay? So the principle of operation for this figure or for this NOT gate is very simple. The second sentence is just vice versa of this one. So you say when the push button is pressed. So when the push button is pressed, then the input voltage is 0 volt. So whenever we press the push button, remember that we say when you press this push button, then it will make contact. So because we have contact, there's no any resistance. This will be acting as a wire, right? So all the 5 volts will be flowing towards the ground. So the voltage, the potential drops across this one, because for this push button, the resistance will be 0. So if you have resistance of 0, no potential drops at that point. And then she said that when this 0 volt is fed to the first pin of the NOT gate, the NOT gate invade it to 5 volt. So the input of the NOT gate, when the push button is pressed, the input to the NOT gate is 0 volt, but the output is 5 volt. Okay? So once you have 5 volt at the outputs of this NOT gate, then the LED will be on. So we say the status of the LED, the status of LED is on. Why? Because the supply voltage of the LED is 5 volt. 5 volts is enough to turn on the light emitting diode. Remember that the pull-up resistor network and the LED, these are just simple inputs and the outputs we may use in the just to check or to verify the truth table of the logic gates. But the input might be a sensor, might be a digital, just we call this a pulse generator. So we can have various. Sometimes it might be even we have electromechanical switch that actually interface the low power DC system with the high power AC system, either single phase or 3 phase. So this is just a simple concept or a simple way of verifying the truth table of the NOT gate that you've been learning in theory. So actually, that's what we need to know for the practical. So when you go for the simulation software, we'll draw this schematic circuit diagram. And once we draw this schematic circuit diagram, then we can just test it and check if it's working or it's not working. However, that in most of the simulations, electronic simulation software, you won't find a NOT gate in this structure. You'll be just find the NOT gates which has only two terminals. One is input, the other one is output. That's all. Okay? But physically, when we do the physical implementation, we'll have a NOT gate which has 14 pins, and then we need this pull-up resistor, and also we need this push button. We need also to have what? To have this current limiting resistor and light emitting diode, just to verify. So you can test the first NOT gate. This is the same, or this is the configuration. You may also change the input to be supplied to the steady pin, which is the first pin, with the input pin for this NOT gate. And this one you can disconnect and connect the first pin of this NOT gate. Right? You can also disconnect it and connect and check just to verify the two-step by using this NOT gate. You may use 1, you may use 2, you may use 3, or you may use any of the NOT gate. That's why this physical appearance is very important for the mind of any serious engineer and any serious technician. Class, are we together? Are we together? Sometimes you may have a system which actually have 6 sensors. One is temperature sensor, the other one is just a humidity sensor, the other one is actual vibration sensor. So once you have a single integrated circuit like that one, you can interface them and you can use them effectively. So that's all about the NOT gate. We'll discuss about NOT gate in simulation and also in hardware. But for the part of the theory, that will aid you to understand the simulation and the practical. This is all about what you have to know in a simple and clear language. In case you have any question, you may ask about what we've discussed. And that's why I taught you the concept of pull-up resistor network. We still have also, because we said the input may be either pull-up resistor network or pull-down resistor network. So today or in the next workshop, we have discussed about pull-down, because this one sometimes you might find that when they push button, for instance, for some of the gates, when the push button is not pressed, you find that the LED is on. So it's better for you to know about pull-up resistor network and pull-down, because it will make you actual to understand how you can use them interchangeably. Is there any question about NOT gate? No. So I would like to say that this is the end for the lecture 3 about, or workshop 3 about basic logic gates, and especially about the NOT gate. So I would like to ask you to join me in the next workshop, where I will be discussing about other 2 types of basic logic gates, and especially in practical context. So nibonyeze hapo, ajui sasa, samahani kidogo, mafundi mitambo wangu.
Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania. Tanzania.